Monday's class was predominantly on electricity. We are going to use electricity here, but only in service of how we are looking at magnetism. So looking at how various things interact, hopefully helping you visualize some of the fields that we've talked about in static images on the screen. They're still going to be on your screen, but now they're at least hopefully not going to be static. And we've got a couple of different iterations, both currents here, looking at different things, and some other equipment over there. Is that a question? All right. So magnetism is this often misunderstood process where we have attraction and repulsion between things, and it comes from the motion of charges and that generating currents, and those currents generating magnetic fields that can affect charges that are in motion. And it can be hard to see, for instance, if you have just a little permanent magnet. So this is a gimbal mounted magnet. This is a magnet conveniently on a stick. What exactly is it in this solid block of magnet that is in motion? And at a molecular level, we have little tiny orbitals of atoms that, or of the electrons in the atoms that are creating that, and lined up, that little tiny current can generate a big effect. We get similar things by taking, lots of electrons and moving them over macroscopic distances. So remember the charge of an electron, 1.6 times 10 to the negative 19 coulombs. And so if you have an amp, a coulomb per second of current, then you're talking, 10 to the 19th coulomb or electrons flowing in that current. And so the macroscopic effects that we see of magnetism are built up out of these little tiny effects from lots of little tiny contributions. And so I have a couple of different, as it were, setups so that we can see some of these effects. So I have one wire right here that I can run a current through. And let me move that, that you can see that. And I'm going to try and split screen and show two cameras at the same time. And that's the, all right. So hopefully you're seeing the same camera, or the same wire being displayed now. Is that kicking in an echo? Hold on, let me mute that echo. Can you still hear me? All right. But I'm getting an echo. Are you getting an echo? All right. If you're not getting an echo, I won't worry about it. I'll just listen to myself talk. So we have a wire, and I'm going to run a current through that wire. And I have a small magnet that I can move around the wire, and as I move it around the wire, this magnet's mounted on a gimbal, which allows us to visualize the magnetic field and kind of see it at any point. Now, if I turn the current off, then the magnet does have a kind of default orientation. It's picking up the magnetic field of the Earth, but when it's here and then I turn the current on, that makes the magnet flip around and shows that local magnetic field here. So if I'm down below, notice the blue end and the red end is on this side, and then I come up to this side and it flips around, and you can kind of watch that magnet flip as we go around the wire. So this shows a circular magnetic field around the wire. So I'm running the current along the wire, the magnetic field is curling around. We've talked a lot about this right-hand rule several times, but this is showing it actually, the magnetic field looping around that wire along the entire length, rather than doing it just with individual. Let me. Nope. I'm sorry. All right, we're going to go just with that camera to there. Nope. Let's start with the simple one. So we have now just a wire, and I can run a current through this wire. I'm not currently sending any current through there, but I have a little shaker, not of pepper, but of iron filings. And so I can spread these around and just kind of randomly distribute them. And the initial effect here is we see not, they're just kind of spread around. But if I run that current now through that wire, it's going to come up, go across, and then go down on the other side. When I initially send that current in, we don't immediately see much effect. Magnetism is usually pretty weak, but if I tap this, then as those things fall, they tend to align with the magnetic field, and so we start to see these circles forming as a result of, the iron is jostled, it can fall. As it falls, it tends to fall in a way that aligns with the magnetic field. And what started as initially just kind of a disordered collection, now we're starting to see these field lines as they come around the wires. Now, the wire up here at the top is not having much of an effect. It's far away and the magnetic field goes as distance. And so I get better alignment in here close than I do further out, even though I have more iron there. If I keep tapping it, kind of get a little bit more, but another way to get a little bit more is to utilize more turns. And so rather than having just one wire, if we look at the magnetic field of a solenoid, now I'm going to go ahead and run that one. And if I probe that with the magnet probe, so that's in there, if I turn it off, that just kind of sits measuring the Earth's magnetic field. But when I turn it on, oh, my hand is blocking your view. So there it is, off with that little red and blue in there. Let me come in from the other side. energized. We see the magnetic field points along the coil. We can get a more in-depth view locally. Again, I'm going to sprinkle iron filings around. If you ever get this kind of setup, don't combine your iron filings with your magnet probe. It just makes a giant mess of your magnet probe. So now we have the iron filings again. And there, as soon as I turned it on, we got a little bit of alignment of the iron filings with the magnetic field inside the solenoid. If I tap it a little more, you see that effect start to build up. And so we have straight lines where the magnetic field is just kind of running right through the solenoid. And then at the edges, it starts to fringe around. And so this is where it's looping around to the other side. And if you look right near any one of these wires, you'll see little tiny circles around each wire that are building up this overall bigger shape. Knock some of them loose, but these circles here are going around each of these wires, so that right-hand rule is still valid in all of the cases. It's the combination of the right-hand rule from those individual coils that gives us this effect of the solenoid, of showing the magnetic field going along and then looping around. And I'm showing it in 2 dimensions, but it's also coming out here, looping up and over. It's also coming out here and looping underneath and going around. And so this effect of the magnetic field there is pervasive in space. It's in multiple sides. Now, this is built up as a solenoid, but we can also have now, oh, sure, question? So I'm sending current in here, and I'm pulling it out here, and then it matters which way the coil is wound, as it were. And so I would curl my fingers in the direction of the coil wind, which are actually that way. And so the field is coming out on this side and going around in on that side. The iron filings don't do a good job of illustrating that. They just line up, but they don't point north versus south. But I can zoom out a little bit so you can see where the current is coming in and where the current is leaving on that coil. Thanks for the question. So now we've got, I'm going to run these ones in series, so it's the same current through both, and in one side I have one thick wire, and on the other side I have lots of little tiny wires, but the total resistance of the circuit is set by the sum of the resistances, and so I really get the same current in both of these. And energizing that circuit. And here we see, even before I tap the circuit at all, we immediately got enough of a change in the magnetic field that we see those circles starting to line up. And a magnetic field always acts perpendicular to the velocity of a particle. And so because the force is always perpendicular to the displacement at that moment, a magnetic field can do no work. However, a changing magnetic field can create electric fields, and electric fields can do work. And so a magnetic field by itself can't do work, but if you're changing that magnetic field, that's where you can get work out of that effect. So I'll turn that back on, and as I tap it, you can kind of see that strong magnetic field from the multiple coils really suck the iron in and kind of right in close. So the fact that the iron is building up right around our wires lets us know this is a ferrous material. It's attracted to that magnetic field. It's energetically favorable for that iron to get closer in that situation. And it wouldn't be physics if I didn't set something on fire occasionally. I'm not sure what's smoking there, but we're not going to use that circuit anymore. All right. Luckily, I have other circuits. Let's pop back to this one. Nope. This one, and I want to show that in two different ways. So we're back to the wire kind of spread across and now I'm going to add another piece, not just a current, but I have a handy dandy magnet on a stick. And so there's no force on the wire by itself. What we see here, it's not a ferrous wire, there's no nickel in there. This is a fairly strong magnetic field. This is a rare earth neodymium magnet. But if I run a current through this wire, then the current is affected by the magnetic field. And so you can hopefully hear it turn on and off. And I can actually feel the magnet react a little bit too, but we're displacing that current. Now, if I turn this over, we can still get that effect. And on this side, I hope you can see it's going one way. And on this side, so if you look at the top-down view, you can see the wire deflected a different way depending on which side of the magnet is up. So with this side up, it's deflected away from me. With this side up, it's deflected towards me. If I take that same side and put it on the other side of the magnet, now it's deflected away from me again. If I then flip it over that way, it's pulled towards me again. Now, physical magnets like this have fringing magnetic fields that come up and around, and so the analysis can get a little cumbersome, but the hope here is that you can see this effect of the magnetic field causing a displacement in the wire and interacting with it. Now, we could work out, based on I'm sending current this way through the wire, if the deflection of the wire is towards me, then my V cross B is towards me. That tells me that the B is down. So this is the south face of the magnet, and this is my north face of the magnet. Now, when you're just using this to stick artwork to your refrigerator, you don't really care so much about the north and the south, but it does end up having the opposite effect on the sign. So I can deflect one way or the other. The other way I could change the deflection would be change the wiring and run the current the other way through this wire. But I'm going to leave that as an exercise in visualization and move on to a new one. Let's go back just to that one. Nowadays, a lot of meters are digital, but what we have here is an old analog dial meter, and we are measuring the voltage pickup on this cube. And so I showed forces on magnetic fields, and I talked briefly about changing magnetic fields. Now, if I just slowly put this magnet in the coil, it doesn't have a big effect. That's a slow change. But if I rapidly change the magnetic field by pulling that magnet out, then I see an effect, and I'm measuring a transient voltage. Now, just leaving the magnet in there, I'm not going to generate any magnetic field. It's not enough to have a magnet in a coil. I need to be doing something that changes the magnetic field inside the coil. And so when that face goes in, I get a current, voltage going one way, a current going one way. When I pull it out, the voltage has the opposite sign. The current is going the other way around the coil. If I go in and then keep going all the way through, that's this. So let's try and do that smoothly. In, deflects, keep going, deflect the other way. In, out, deflects the other way. So seeing this face come in and then that face coming out looks the same to the EMF as seeing this face go in and then continue through and coming out the other side. Now, I haven't changed the face. I've got the stick there so that I've got a consistent face. This is deflecting to, when it first comes in, that's going negative, and when I pull out, it goes positive. If I come in from the other side, I'm going to get a positive deflection and then a negative deflection. I've changed the sign of the voltage by changing which side I come in on, or, and now I'll actually flip. So initial deflection is positive, initial deflection is negative, pulling out is positive from that side. If I change my magnet around, now I get initial positive and the pullout is negative. We didn't get much into LC circuits or LR circuits, or the various combinations of different circuit elements, but this meter has a resonance, and I could, if I go really fast, I'm getting a big change, but the meter can't react at that speed, whereas if I make a slightly smaller change but time it to the resonance of the circuit, I can actually match that and drive on resonance and get a bigger amplitude than I would from just one sudden change, a smaller on resonant change. Now, that's not just the magnetic field, that's the combination of the magnetic field and the various resonances that are happening in the oscillation of this, if you remember back to Physics 31. If I have the magnet in there, and I turn the magnet, I'm spinning the magnet along its axis, I'm changing the magnet, but I'm not having an effect on the magnetic field. The magnetic field that was coming through rotates, but it's still coming through. If I really wanted to get a good effect, rather than spinning this way, I would flip it end over end, which is hard to do with a stick. But that sudden flip all the way around can give me a pretty big change. So I don't have to have the magnet go in or out of the coil. It can be sitting in the coil and just rotating. Or I can have a coil sitting in a strong magnetic field and rotating. And this is how we make generators work, is have something that's producing motion that we can harness to make into changes. It's also how engines work, motors, where we drive a change with that current. So this is an example of induction. I'm using a changing magnetic field by moving a magnet in or out of a coil. Now, this coil has lots of turns, several thousand. And so I'm using that big N to make a big area. The area of this coil is not just, at 3 centimeters pi r squared, but 3 centimeters pi r squared times the 2,000 turns of this coil. And so that gives me an easier time of getting a measurable effect on the voltage that I'm generating. And I still have to have a lot of turns and a pretty powerful magnet to get that noticeable change of just a couple of volts. Questions about any of that? I've got a new message that I can't see. All right. Do the coils have to be insulated for this to work? Excellent question. Yes. The coils do have to be insulated for this to work. If the coils are not insulated, if I have a bunch of wires curling around and they're all insulated, then the current has to go through this one, then this one, then this one. If I don't have insulation on that, then the current's not going to go the long way around. It's just going to go and short circuit it. So to make this coil work, I can actually bring this up close to the camera. So you can see the very fine wire that's being used there. This is called magnet wire because it's wound and it has a fine enamel coating. And normally you have to scrape it off with sandpaper or you use a chemical to remove it. So there's a thin copper core inside of that, and the wire is insulated. If it was bare copper, it would be more yellow. This is a red enamel coating that is insulation. I would have a much, much lower resistance if I shorted it out and let it just go straight rather than having to go through the probably more than a mile of current there. Thank you for that question. Other questions about what we've seen so far? I've mentioned a couple of times the magnetic field of the Earth. So I want to show that one. 12. So what I have here is, at first glance, a compass. If I turn this, you can see that the needle stays aligned with the same direction. But I have an additional axis here that allows me, once I've lined this up, I can take it and turn this and allow the compass to rotate in another plane. And the effect there that you see is that rather than staying in this plane, the needle dips into this vertical plane. This is called magnetic dip because physicists are big dips sometimes. And it's a property of the Earth. Now, here in Burlington, Vermont, if you're still in this area, we're at about 45 degrees north latitude, and the magnetic field around the Earth is not parallel to the surface of the Earth all the way around. It actually swings around. If I move this out of the shot for just a sec. So if I replace the Earth with a really strong magnet, right at the pole, we'd expect that the Earth's magnetic field to actually be vertical, whereas over at the equator, we'd expect the Earth's magnetic field to be tangential to the surface of the Earth, kind of running parallel to the surface of the Earth. And at 45 degrees north latitude, we actually get a fair amount of dip in. So here in Burlington, we have some dip, but not as much as the Canadians have north of us. I'm allowed to make that joke because I'm actually Canadian. So this is a way of determining, you could work out the strength of the magnetic field by looking at the different components. So figuring out what it's doing this way and what it's doing this way, and working out the Earth's magnetic field as a result. Sometimes people do an experiment called the tangent galvanometer, where they look at displacing this needle. If I have a known magnetic field and I push, then that lets me know how strong the Earth's magnetic field is that's pushing back. All right, I have a question for you that we're not going to do in learning catalytics. I hear the beeping. I'm going to pop over once I've given you a chance to think about this. So when I turn this, it's currently dipping about 60 degrees. So if this is 0, it's swinging down about 60 degrees. And that's when I'm perfectly aligned with, so my axis of rotation is right along the horizontal component of the Earth's magnetic field. If I misalign this, so now we're there. If I rotate, let me swing it around the other way. If I rotate it now, will the dip be bigger or smaller? So let me type that into the chat, and then I'll look at some of the questions we've had. So what folks are voting on right now Initially, when we measured the dip, I lined the axis of the rotation up with the compass. And I turn this way, and we get about a 60-degree swing. And now my question is, if I misalign it and then rotate, am I going to get a bigger dip or a smaller dip as a result? All right. We are, looks like 25 to 4, 28 to 4, bigger, smaller. Most folks are voting for smaller. So I'm going to turn. And the dip now is about 90 degrees. It's bigger. This is a counterintuitive question, which is why I asked it. So let's kind of talk through what's happening here. When the initial dip lined up, swung down about 60 degrees. If I can't rotate in this plane, but I'm constrained to rotate in this plane, then the field down can pull down, and the field, so now I'm rotating this way. Sorry, let me face you. Now I'm rotating this way. I want to be dipped like this, but I have to rotate towards, perpendicular to that plane. It's trying to line up with this, and the best it can do is come here. It can't go over that way, but this component will still pull it down. And so this three-dimensional vector that's this way, here's the vector that it's trying to line up with, has a vertical component and a horizontal component. If I only let it line up with the vertical component because I've constrained it to rotate in this direction with no amount of the horizontal component, then the result is it's going to take just that vertical component because it can't pick out any of the horizontal component in this way. Let me show that again. So here's the dip needle, and when I rotate it this way, it can line up with the horizontal component and, the horizontal component and the vertical component, and those two vectors add to give me the 60-degree angle. I don't actually, if I rotate it so that it can't line up with that horizontal component, now I'm getting just the vertical component that it lines up with, and the result there is a larger dip angle. All right. Now, I don't mean to imply that if you line up with prevailing trends or not, it makes you a bigger or smaller dip. That's a level of sophistication about society and constructs that I'm not qualified to say. But at least for magnetic fields, you're going to get a larger dip if you don't allow the horizontal component to come in. All right, we got about 10 minutes left. I could draw picture versions of that, but I want to show a couple more things. So let's talk about some of the other demos, and then if we have time at the end, I'll come back to the dip needle. So we talked about induction, we talked about the Earth's magnetic field. Let's do some applications here. Let me pop over to camera 11. Zoom out just a bit more. So what I have here, to start with, this is a big piece of aluminum, just about an inch thick, and I want it thick so that the resistance goes down. Remember, the resistance is going to be a function of how thick something is, and so by increasing the thickness, I can get a lower resistance. And what I'm using this for is a plate to induce currents in. So this is just a coil of wire. It's multiple turns of insulated wire running around and around and around. And then it's connected to just regular 120 volt current. And so the effect of running 120 volts house current through this is that that's an alternating current. So the current is going to go one way, then the other, one way, and then the other. And that current is going to switch back and forth such that it's 60 times this, switching from here to here to here and doing that 60 times every second. So that means this is going to create a magnetic field. This way, that way, this way, that way, this way, that way. Back and forth 60 times a second. A changing magnetic field can create an electric field. The electric field creates currents that create magnetic fields, and those magnetic fields, by Lenz's law, are going to be in opposition. So we're going to try and oppose the change. And this is the same thing that we were doing with the inductive coil and the galvanometer, but now we have a bigger system and I'm running a much larger current through it. And the effect is that we can actually get levitation. And if you've been in Japan on their high-speed bullet trains, they actually use this as a way of levitating things. And so I have a hover puck here that is bouncing and humming at that 60 hertz, but it's the changing field from the current going through there, creating opposing currents in the plate. Now, if I had a copper plate, it would probably float a little bit higher because the lower resistance would mean better currents, stronger magnetic fields that would push back. If I had a copper plate that thick, it would also probably get stolen because copper is really expensive these days. But aluminum is good enough to give me this levitating effect. Now, neither of these things are intrinsically magnetic. Aluminum does not react to a static magnetic field. It's the changing magnetic field from this coil that's setting up currents that's creating an opposing magnetic field. And as one of them changes, the other one changes, so that they're always in opposition to each other. Now, it takes a lot of current to do that. This is actually warm to the touch from running enough current through there. And so this particular version, I would not trust to, have a cool hoverboard or try and run a train on. But if you have low enough resistances that you can get large currents without dissipating too much power, and you have good ways of dealing with the heat, this is a not bad way to get levitation. Now, if I could make this a superconductor, this would float higher, and I wouldn't dissipate as much energy in here, and I could do everything easier. Now, currently superconductors are kind of hard to make, but that's an active area of research, is raising the superconducting transition temperature so that we can, for instance, levitate things easier, which sounds like a good plan to me. All right, I've got one more thing that I want to show. Let's go to just this camera, content only. So this is what's called a Crookes tube. And it's an electron gun. Those of you who grew up with the old tube televisions had something like this in your house. So I'm using a high frequency, high voltage transformer to put that at a really high voltage. I've got a metal plate there, and that metal plate at a high voltage will just start expelling electrons. The voltage is so high that I've piled so many electrons onto that spot that they start jumping off the plate. So right here is my plate. At a high enough voltage, I'm kicking electrons off of that plate. Right here, I have another metal plate that has a thin slit in it. Not thin enough that we have to worry about diffractions, but it takes that ejected cloud of electrons and says, I'm only going to let through the ones that are going in a straight line. Now, what I have here is a beam of electrons, which is a current, but normally when we talk about currents, we've constrained it to a wire. And so if I want to have an effect, it has to move the entire wire. Now, I'm going to bring the magnet near that beam of electrons. And this is that same effect. We have a magnetic field interacting with electrons that are traveling with some velocity. Now, if I turn the magnet around and use the other end of the magnet, now I start deflecting my electrons down. So I can influence that beam of electrons with a magnetic field without actually touching them directly. All right. So does the north side attract the electron or the south side? Guessing south attracts. Remember, let me pop back to the wide view. So the electrons were going this way, and I brought a magnetic field behind them, and that deflected down. So it's never going to be attracted towards or repelled from the magnet. It's going to be perpendicular to the magnetic field and the velocity. And so if this is an electron and it's being deflected down, that tells me that the magnetic field, the V cross B with the negative, so sorry, V cross B. So this is the south face of the magnet, V cross B, and then the negative pushes down. All right, that is 2 o'clock. You're all free to go. Lightsabers and other such fun will be available in advanced physics courses. That's plasmas. We didn't do much with plasmas, but thank you so much. We will have a couple more demos on optics on Friday, as well as a quiz and the final written details on what's on the final, which will be multiple choice with a couple of numerics. I will stick around to answer any other questions that came up during this, but thank you very much for swinging through. Oh,